Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we will simplify or study the simplified mode structure of a step index optical fiber that we discussed at length in the previous modules. In the previous modules, we said that pure TE or TM modes are possible only for the mode order nu equal to 0, and even then the TE0 and the TM0 modes are not the fundamental modes. The fundamental mode happens to be what is called as a hybrid electric mode. We have said that hybrid modes are those modes where there is in general all three components of the electric field and all three components of the magnetic field, depending on the ratio of Ez to Hz. If the ratio is greater than 1, then we call those modes as E modes or E waves or hybrid electric modes. If the ratio of Ez to Hz is less than 1, then we would call them as we would call them as EH modes. Okay. So, those are the H modes. We derived a equation called as characteristic equation, which allows us to find out the values of the propagation constant beta by solving that particular characteristic equation. Of course, the characteristic equation is written in terms of all three unknowns kappa, gamma and beta, but with the known quantities and with the relationships that we know between kappa, gamma, beta, k0 n1, k0 n2, you can convert all those other variables, that is you can eliminate all the variables and essentially solve for either kappa or gamma. Typically we solve it for gamma, and from gamma we infer the value of beta or we calculate the value of beta. I also mentioned that in general the solution of those that particular characteristic equation is actually very complex. Even when you employ good numerical methods, solving for beta is difficult. Even when you solve for beta, the corresponding mode structure seems to be way too complicated for us to think or for us to understand it in simpler terms. Okay. These set of modes, the hybrid electric modes, are the true modes of the optical fiber, because they are the result of the analytical solution of the wave equations that we have actually solved. Okay. So, as such, whatever we have derived in the previous modules are the true solutions or the true modes of the optical fiber, except that, or it is just that they are actually too complicated for us to visualize and work with it. Okay. And moreover, those solutions that we discussed in the previous modules are valid for any value of delta. Okay. However, in practice, in single mode fibers, especially in single mode fibers, the value of the refractive index difference, which we denote by delta, and this delta is sometimes given as n1 minus n2 by n1. So, kind of a fractional difference between the core refractive index and the cladding refractive index. Okay. In practice, this delta is about 0.01% for a single mode fiber. Okay. This value is slightly greater, so about 0.3% for a multi-mode fiber. Okay. However, if you actually look at, instead of the percentage values, if you look at the actual difference, that difference turns out to be quite small. So, we can actually simplify the solution of the characteristic equation as well as simplify the structure of the modes by mathematically taking this delta equal to 0. Taking delta equal to 0 while requiring that V be approximately 1, greater than or equal to 1, okay, is what is called as weakly guided approximation. Okay. The idea here is that since for all practical purposes delta is so small, just about 0.01% for single mode fibers or about 0.3% for multi mode fibers, we can treat n1 almost equal to n2. Okay. So, when you treat n1 equal to n2, at least mathematically you can of course do that one, but physically you do understand that n1 cannot be equal to n2, because if n1 is equal to n2, the core refractive index will be exactly equal to the cladding refractive index and there will not be any total internal reflection. Instead, it is just one big homogeneous isotropic media, okay, where the refractive index is equal to a single value throughout core and cladding. Okay. So, physically that is not possible, but mathematically we can take this approximation because the errors that we make in this approximation turn out to be quite small when compared to the true solutions. That is, if the true picture I mean when you compare the results from the true characteristic equation and the mode structure to the modes that we are going to discuss now and the characteristic equation, the difference is just about 2%. In fact, this difference is not even 2% for modern single mode fibers, where delta values are being driven lower and lower. Of course, delta is lower for long haul standard single mode fiber, but you will see that delta can be quite large, and in fact, the refractive index need not be just step index profile when you have to deal with a parameter called as dispersion and another parameter called as nonlinearity. Of course, the discussion of dispersion and nonlinearity is not we are not going to undertake that one right now, that will be left for the later modules. Okay. But mathematically I want to go with this so called weakly guided approximation, and this weakly guided approximation was originally formulated, okay, by a couple of people. One is A. Snyder. However, the results of the weakly guided approximation or the explicit recognition that this is weakly guided approximation was made from Snyder's results, using Snyder's results by a person called Glog, and there is a very famous paper which I will try to upload it hopefully, and it is very nicely written as well. So, you would be able to read it and understand more about this weakly guided approximation, and this famous paper was published in Applied Optics. It is a journal called Applied Optics in 1971. I will give you the full details over the course website. Okay. So, whatever we are going to discuss in this module is all due to the work of this person, and we are going to look at what exactly he did that. Now, before we can do that, let us recapitulate the true mode cutoffs, right. So, when we say cutoff, what we mean is that is the frequency at which the mode would just begin to propagate, or it is mathematically possible that the mode would just begin to propagate. Of course, you do not want to operate at the cutoff, you want to operate far from the cutoff, right, because you want to be able to support that particular mode. That mode has to more or less carry information. So, you do not want it to be barely propagating, you want it to be well propagating, it must have a large propagation constant. Okay. And how, of course, that is the ideal thing, but you also need to know where these cutoffs occur, right. And those cutoffs we have already discussed for the TE0 mode and TM0 mode. If you look at, then they are actually the roots of the Bessel function with the parameter kappa in the argument, and I do hope that you remember what kappa is. So, wherever this kappa times a can go to 0, okay, then not 0, when values of kappa a is such that the Bessel function of the order 0 goes to 0, I mean Bessel function of the order 0 goes to 0, which is correct, okay, then you will have these different TE modes. For example, if I plot with respect to kappa a, okay, this Bessel function of order 0, how would it look like this Bessel function? This would look something like this. Okay. So, it starts at a value of 1 and then it looks like a damped sinusoid as we have discussed. So, at this point it is 1. So, where are the roots of this equation? These are the roots of this particular equation. So, once you reach these roots, you will start seeing different TE modes. So, you will actually see TE01 and of course TM01, both modes occur at the first root of the Bessel function J0, which occurs around 2.405, okay, or maybe 2.408, does not matter. So, it basically occurs at just after 2, okay, and then the next time when the J0 function goes to 0 is after, I mean very close to 6, okay. So, it is slightly less than 6, but it is very close to 6. At that point you will have modes which are TM02 and TE02 modes and so on. So, more modes appear as the value of kappa increases, but remember, as kappa increases, the corresponding value of beta is actually decreasing, because kappa and beta are related. Kappa square plus beta square should be equal to k0 square n1 square, right. So, you do not want to go too far into this kappa a regime. When you do that, you will actually have lots of modes to deal with, and for communication, dealing with many modes can be a blessing or it can be a curse. Most of the times it is curse, but with sophisticated signal processing algorithms, these different modes are now being used to increase the capacity of the optical network in something what is called as a mode division multiplexing. Anyway, these are the topics that we are going to discuss later on during the course. So, it is good in some sense to actually work with many modes, but that many mode propagation is not for long distances. For long distances, you are only mostly looking at a single mode operation. Okay. So, you would again, as I told you, you would expect that TM0 or TE0 modes are the fundamental modes, because their cutoff is occurring at say 2.405, but please remember, only when your kappa increases, kappa A increases beyond this value, then these TM01 and TE01 modes actually start propagating. So, for this region there are no TE or TM modes. It turns out that there is another mode called as hybrid electric mode, okay, the HE mode, and with an order nu equal to 1, right. So, these HE modes are the roots of the Bessel function of the first order. So, they are the roots of J1, and in this case you have to include the origin as well. Okay. How would this look like? So, let me erase all this. I hope you have copied this one, or you can go back to the video and then look at these things which I am erasing now. But when you look at the Bessel function of order 1, okay, it goes something like this. So, again in terms of kappa A I am plotting this. Bessel function starts, or Bessel function J1 order 1 starts at 0 at the origin, and then it keeps on going something like this. Okay. If I were to plot that Bessel function here, then it would look this way. So, it has to start at this point and then go over the route for J1. Yeah, so it must go something like this. Okay, so it looks again like a damped sinusoid signal, but its root is between the J0 roots. Okay, so first time you will have a J0 root, then you will have a J1, then you will have J0 root again. So, maybe I made a small mistake here. So, this should have gone after that, but anyway, if I do not write it both on the same graph, just write them here and then mark the points, you will be able to understand where the roots are. Okay. The roots of Bessel function J0, the first root occurs at 0 itself, okay, and for HE11 that is actually allowed. Okay. However, the roots of EH modes also are EH1 modes also are the roots of the Bessel function of order 1 itself. So, you would expect that EH mode also to be present here, but unfortunately that is not the case. You can go back to the characteristic equation and then show that the solution when you take kappa A, or when you take kappa A equal to 0, will not be satisfying the characteristic equation for the EH modes, okay, whereas for the HE modes that solution is perfectly valid, okay, and therefore HE mode can occur right away just when kappa A becomes greater than 0. Okay. So, which means that this particular mode has no cutoff frequency whatsoever. So, the cutoff frequency for this mode is actually at 0. So, this is the mode which would be HE11. The next 0 for this J1 function occurs slightly less than 4. Okay. So, the next 0 when it occurs, you will have HE12 mode, but at the same time you will have only HE12 mode. Okay. So, you will also have the EH11 mode. So, you will have EH11 mode. Okay. So, you will have HE12 mode, you will have EH11 mode, and it turns out that for HE nu m modes with nu greater than 1, okay, the roots of Bessel function J nu minus 2 kappa A are the cutoff frequencies. So, when you have HE nu m with nu greater than 1, then the roots of J nu minus 2 of kappa A will be the solutions. Okay. So, because this is the solution, which means that if you actually go back and then take a look at where J0 is going. So, when you set nu equal to 2, this will be the roots of J0 kappa A equal to 0. Therefore, wherever TM01 and TE01 modes are there, because they are the solutions of J0 function going to 0, at that time you will also have a solution which is HE 1. Okay. So, you will have at 2.405 3 modes HE21, TM01 and TE01. Okay. Then the next route will actually be at around 4, at which point you will have 2 modes which are HE12 and EH11. Okay. Then you will have modes which are say HE22, then you have TM02, you have TE02, and you will also have, so at this same HE12 mode you will have EH11 mode, and you will also have HE31 modes. Okay. Because for nu equal to 3, this would be the root of J1 kappa A equal to 0, the second root, and therefore this would be HE31 mode as well. So, these are the modes that you get from solving the true solution or the true characteristic equation. So, these are the proper modes and this is the mode hierarchy. So, the fundamental mode is HE11, then you have 3 modes which are TE01, TM01 and HE21, and then you have modes which are HE12, EH11 and then HE31 and so on. Okay. If you look at them carefully, you will see that HE nu plus 1 m mode is actually degenerate with EH nu minus 1 m mode. Okay. So, these two modes have the same propagation constant and therefore, we call them as degenerate modes. Okay. And it is by combining these degenerate modes, we can actually land up in what is called as linearly polarized modes. So, what is this linearly polarized modes? Well, I have mentioned to you that the true solution will give you these modes, whatever the different modes that we talked about until now, but those modes are actually quite complex to visualize, and in fact, if you change the profile a little bit, then the modes actually become very complex. Most importantly, they also have non-zero values of Ez and Hz. But I have also told you that in practice, this value of refractive index difference between the core and the cladding is so small that for all practical purposes, we can assume that N1 is equal to N2, which may be equal to some value of N, let us say. When you make this assumption, delta is equal to 0, kappa will be equal to 0, gamma will be equal to 0 and beta will be equal to K0n, where n is the same value of N1 and N2, that is it's the same value throughout core and the cladding. Okay. So, this is the weakly guided approximation. Now, if you look at our first, or if you go back and look at our first few modules, you would have come across what are called as plane waves, right. So, in those plane waves or the transverse waves, it was possible for us to actually have linear polarization. That is, you had a situation where if I were to draw the polarization axis in the x and y, it would follow a particular line. The inclination of that line was dependent on the ratio of Ey to Ex, but because it was actually the tip of the electric field vector was along a particular line, this was called as a linearly polarized wave. Okay. So, in a manner very similar to that, when you take delta equal to 0, it is possible for us to combine the true solutions, okay, have a linear combination of the true solutions and obtain a situation where the longitudinal components Ez and Hz are so small that they can be neglected, and therefore, the electric field components, instead of being talked about as the r and the phi component, you can then convert the r and phi cylindrical coordinate components into x and y components and essentially end up with what is called as a linearly polarized modes. Okay. So, you can abandon in some sense the circular coordinate or the cylindrical coordinate system and replace it with a rectangular coordinate system. Okay. When you do so, you will actually end up in what is called as linearly polarized modes, and these are in general written as LP LM modes. Okay. These are called as LP LM modes. This fellow will tell you how many radial nulls you have, or the this one you have, and M tells you the azimuthal half angles or half sinusoids that you have. Okay. So, these can actually be postulated first, that is what Glock did. He assumed that the fields could be entirely along Ey, okay, but he also said that this Ey, which is still a function of r and phi, no problem about that, would follow something like this. It would be of different orders L now. Okay. So, you have JL again with some kappa r inside the core, right. Outside the core, of course, you will have KL and gamma r. Okay. You might be surprised to see this Bessel function type of a behavior, but that is fine because we are not really looking at the components in r and phi, we are looking at components in x and y, right. So, this is a very important simplification that we are able to make, and then this Ey of r comma phi corresponding to the Lth mode would look something like this. Before the z, let us put down the cosine kind of a thing. Okay. So, he postulated that it is possible for us to actually assume cos or sine, does not matter whichever you can assume, then there has to be a corresponding cosine and sine here as well. And then he used Maxwell's equation to show that Ez, which is really proportional to the derivative del Ey by del x, will be kappa times electric field Ey, and we already know that in the approximation delta equal to 0, kappa truly is equal to 0, but if delta is not exactly equal to 0, approximately 0, then kappa will be approximately 0, and what we have just figured out without solving the equations of course is that Ez will be very very small compared to Ey, because Ez is kappa times Ey, and kappa in the linear or in the weakly guided approximation is actually equal to 0. So, this is the basic idea behind linearly polarized mode. I showed you with Ey expression, but it is true if you assume that the initial field is Ex. In fact, you can calculate what are the other fields Ex, Ey, Hx and Hy. You will see that when you assume Ey to be non-zero, then there will be a corresponding Hx component. If you assume Ex component, then there will be a corresponding Hy component, and of course, in general you can have a linear combination of x and y. Okay, this is very important. You can actually have a linear combination, which means that the phase between these two components will not be equal to, will not be some complex number, it will be just equal to 0. So, the waves are not circularly polarized, the waves are linearly polarized. Okay. So, this is a very important thing, and these modes, as I told you, are described by LP-LM. Okay. The corresponding characteristic equation can also be simplified. It goes something like this: kappa j L minus 1 of kappa A in fact, divided by j L of kappa A again, must be equal to minus gamma k L minus 1 divided by k L. Of course, the argument of these guys are gamma times A. Okay, and cutoff conditions are obtained by setting gamma to 0. Okay. When you set gamma to infinity, you are far away from the cutoff, but when you set gamma to 0 or gamma tending to 0, you are near the cutoff, and you can actually show that the solutions of this one, of this characteristic equation, will lie between zeros of JL minus 1 and JL. Okay. So, with an argument x, where x will be equal to kappa A. So, the solutions of kappa A will always lie between the zeros of JL minus 1, that is L minus 1th order Bessel function, and JL function, which is JL function, the Lth order Bessel function. In fact, these LP-LM modes can be related to the hybrid electric and hybrid magnetic modes as well. So, for that purpose, let us actually write down the Bessel function in both first order Bessel functions, because most of the time that is sufficient for us. So, Bessel function of 0 starts at 1 and then goes to 0 at around 2.4 here, and then next time goes to 0 at about 6. Okay. So, this is very nearly 6. So, please excuse the way I am drawing these pictures. These are not the correct pictures, but you can look at these pictures in the paper or in the textbook. So, you will be able to appreciate this one, right. So, we have seen that the characteristic equation with L equal to 0 will have solutions at j minus 1 divided by j 0, right, and you are looking for the solutions where of this j minus 1 fellow, okay, which means that including the origin, because j of minus 1 or Bessel function with an order minus 1 is actually minus Bessel function of the order 1. So, this is from relation between Bessel functions, which you can find out, and what you actually see is that you will see the solutions of J1, right. So, of course, I have to draw now J1 here. So, this is my J1. The first solution or the first equation starts at the first point at the angle kappa or at the argument kappa A. J1 will be equal to 0, and then it starts to change, increase, and then go to 0 at around 4 or maybe slightly less than 4. Okay. So, do not worry about that, and then it will go to 0 later on. Okay. So, this is for LP L equal to 0 and LP mode with L equal to 1, and the corresponding solution sets are. So, this is one region, right. So, let me use a different color. This is one region where the solution is only coming from this one, and the solution here is LP 0 1 mode, 0 standing for L equal to 0, and once you get J 0 going through the Bessel function 0 J 0 going through the 0, then you will have next set of solutions, and this next set of solutions will be valid until the next root of J 1. Remember, kappa A has to switch between J L minus 1 and J L. Okay. So, in the next set you will have the mode which is LP 1 1 mode, but from our previous discussion you also know that in this range you actually have ended up with the true solutions which is TE01, TM01 and HE21 as well. So, what you can actually see is that LP11 is a linear combination of 3 modes TE01, TM01 and HE21. Okay. So, by combining appropriately these 3 modes you can actually obtain different LP02 modes. Of course, next time when the Bessel function J1 goes through 0, you will have LP02. So, this is the solution, and at that point you are looking at LP11. So, this is J0, right, and this is J1, and this should be 1 less than that. So, LP11 mode is the one which is actually TE01 or TM01 or HE21 combination, and if you actually look at how this would look like, you will have, it would look something like this. There are 4 possible solutions. So, one indicates that you actually have one half circle, okay, actually 2 half circles. It is always the double the number of half circles in one, and this one indicates what is the ring structure or the number of rings that you have. So, you actually have an appropriate number of rings. So, LP01 mode of course will actually have at the center it would be maximum, and then it would actually gradually go down. So, I can't draw this one, but intensity goes down, and this one indicates that there is no phi dependence, okay, whereas this indicates the number of rings to be equal to 1, number of circles to be equal to 1. So, these are some modes. What I will do is I will upload different mode pictures in the website or in the assignment for you, or you can look at textbook and you will be able to find out these different modes. Okay. So, this concludes our discussion on LP modes, but please remember that LP modes are not the true modes, but the true modes can be superimposed in order to form the LP modes. Okay. Thank you very much.